We're talking about linear regression and how we can fit a line that goes through data written in the form of Y versus X. X in our case is advertising expenditure and Y is sales. We have lots of points and we're trying to find a line that best goes through all these data points. And what we're looking at is the idea that there is a difference between the line and the points. The line is the prediction and the points are the actual data points. So the difference between these two is a prediction error. This error should be minimized. So let's begin with understanding how we can find this error. We have a line, we need to represent the line, and then we need to represent the error. So how do we find this error? Some notation here may help sort of fix ideas. Y, as we've been seeing so far, represents the response, which is the actual sales. And you can see here yi hat. The symbol on top of the Y that you see looks like a hat. And in fact, statisticians and machine learning folks call it a hat. Yi hat is the predicted value of Y. It lies on the line, whatever be the line. In fact, there are more advanced models in which it lies on something that is not a line. Yi hat is a generic notation for predicted value. So yi minus yi hat is the error. And this error could be positive or negative. And the aggregation of these errors, one way to aggregate these errors is by simply taking the average error. I can also work with totals because n is fixed. But let's stick to this. This is an average error. This is an average error. Is this okay to work with? In other words, simply finding a minimum value of this error as defined in this way, is that okay? However, I know that this error is sometimes positive or negative. So if I simply want to minimize this, I will just take yi hat to be as large as possible. But that's not the idea. What you want to minimize is not the error mathematically, not yi minus y hat, which could be positive or negative. What we need to minimize in some way is some magnitude of the difference between these two things, whether it is positive or whether it is negative. A high positive number is not good and a high negative number is not good. Yi minus y hat should be close to 0. It should not be too large and it should not be too small. That makes this slightly complicated and we cannot directly add the errors without modifying them to capture this idea that they shouldn't be too large, neither should they be too small. One way to deal with this is to ignore the sign of the error. Is to say, if the error is plus 3, in other words, between actual and the line is plus 3, I'll take the error to be 3. If it is minus 3, I'll also take the error to be 3. In other words, whether I'm under-predicting or over-predicting does not matter. In both cases, I will treat the error as positive. In other words, too high a prediction is bad, too low a prediction is bad. And I capture that by taking absolute values. Just to remind you, an absolute value ignores the sign of a number. The absolute value of 3 is 3. The absolute value of minus 3 is also 3. So this works. But there is a problem here. I still do not have an answer. To get an answer to my equation, I now need to put in the line. And the line is this prediction, yi minus yi hat. And this line is written in terms of b0 and b1 xi. Now I have a well-posed equation. My prediction has been replaced by the line, and I can ask myself the question, can I minimize this definition of error, which is the average of the absolute error of the observation from the designated line? And one way to do that would be to find a b0 and a b1 such that this expression of error is the smallest. And the question then arises mathematically as to how to minimize this error. Now here a little bit of history would help. Historically, linear regression came about quite some years ago, early on in the 19th century, where many of these calculations were done by hand. And so the ability to manually compute or have an algorithm that could be done within reasonable computation time was important. Today, it is less important. And today, in principle, I can minimize this error just as easily as any error. And as we'll see a little later, this error or this kind of calculation on absolutes is in fact done. But one of the reasons it isn't the way regression is done is because of a certain difficulty that arises when I work with absolute values. So let's suppose that I do need to find the values of B0 and B1 that yields this minimum error. But to find a minimum, as I said, we can either search over all the values of beta0 and beta1. And for example, in machine learning, we have search algorithms like gradient descent and grid search, etc., that allows for that to happen. But this was not possible when linear regression was done in years past. And so the way minimization was done was by using calculus. And in calculus, the way things got minimized is by differentiation. To differentiate something, to do calculus with it, means to say I differentiate something with respect to beta0 and beta1, and I then set the derivative equal to 0. Minimum means that the slope has to be 0, and that's a question of calculus. But if I do that with the absolute function, it does not have a slope at 0. In other words, this is not differentiable. So I cannot use calculus to minimize my absolute error function. Not a good reason today, not a good reason in the 21st century. But there are other reasons why we're going to do what we are going to do. But one of them is computational. So, because it is mathematically inconvenient, we go towards something that is differentiable and for which we get nice closed form algebraic equations to solve, quick computation, well-defined answers. And that fix is that instead of taking absolute values, we take squares. It does the same thing. The square of 3 is 9. The square of minus 3 is also 9. Minus 3 into minus 3 is 9. So taking the square of a number also removes its sign. What it does do, and this is not so nice, is that it blows up large prediction errors. And that is one of these things that people in regression analysis worry about when checking assumptions. But when we do squared values instead, we can now work this through in a calculus-oriented way and solve our equation. As before, this accommodates positive and negative errors. It is differentiable. The math goes through, and I will be able to do exactly the same calculation as I did this time. Last time what we had is we had absolute values. Now we're replacing that with squares. We're also replacing yi hat with my equation b0 plus b1 xi. This expression is what I minimize in order to get my b0 and b1. This is the usual way of doing simple linear regression. This way of finding b0 and b1, in fact, is called the method of least squares. Squares because I'm squaring the prediction error. Least because I'm minimizing the average of these squared errors. This is the method of least squares. The method of least squares is used not just in linear regression, but in a large class of algorithms used widely in machine learning and in artificial intelligence. It is probably one of the commonest algorithms that is used in order to minimize things. The complications arise are computational in nature. if the model becomes very big. But the principle is very often the same. This is what gets to our answer. So the math problem is, you know all the x's, you know all the y's, this comes from the data, form this equation, minimize this, get the smallest value of this error. The corresponding values of B0 and B1 are what we are reporting as the coefficients of simple linear regression.